I want to start by thanking the organizers for this kind invitation. Today, I will not talk about my own work, but mostly about what we discussed last Thursday and Friday at a workshop we organized here at Wake, where we focus on black hole spin measurements across the spectra. And I want to also thank Delilah for helping me to brainstorm what to say today. And I also hope I provide a fair but broad picture of what we know about black hole spin measurements. So let me take you all for a spin. So we're interested in measuring the spin of astrophysical black holes. This rotation refers to dragging of the space-time around the black hole. And according to general relativity, our best theory of gravity, astrophysical black holes are only described by two parameters, their mass m and their angular momentum j. As for the charge, is negligible for macroscopic objects. The spin in this context is therefore a pure gravitational phenomenon with profound effects on the environment, so we want to measure it for several reasons. For example, due to its diagnostic power. The spin is a sort of memory of how the black hole was born and grew. For example, a black hole that grew primarily by accretion gas in a steady direction tends to end up with a high spin. So it is telling us about the memory of it. The spin strongly affects the efficiency of converting mass to energy. So for instance, a rapidly spinning black hole, its heat goes very close to the event horizon, so the gas accretion can fall deeper into the potential well and thus releases a lot of energy as radiation. So the spin essentially also sets how luminous an accretion black hole can be for a given mass supply. Spin is thought to power relativistic jets, as the one we just heard an hour ago by the beautiful talks of the BEX Japan AGN working group. And this could be through the Blandford-Senja mechanism. A high spin, black hole spin, can launch powerful jets. So a spin might help why some black holes produce jets and why others don't. It's been induced dragging, the frame dragging can cause their inner accretion disk and any jet to actually precess or align with the black hole equator. So we also want to understand that. And to do the spin, it is expected that black holes play a role in regulating star formation in the host galaxy, and this is typically known as AGN feedback. So in summary, the spin is a crucial parameter. It affects energy output, feedback into the galaxy, and encodes the evolution of the black hole itself. So measuring it informs many areas of astrophysics, and that's why measuring the spin of a black hole is one of BEC's main core goals. But because of this tremendous importance, it is no surprise that we have several methods to actually do these experiments, to actually measure these crucial parameters. So for example, and this include, and there are actually experts on this call, way more that you can ask all the questions about these methods, starting, for example, with the continuum fitting method using stellar X-ray binaries, where we assume we have a geometrically thin, optically thick disk emitting as a multi-temperature black body. So by modeling the thermal spectrum, one can infer the inner radius of the accretion, and there is a one-to-one correspondence with the spin. And therefore, we can, in principle, measure the spin using that technique. Also, from the early days of black hole studies, it was realized that there must be a hot energetic corona above the accretion disk that produces the observed hard X-rays, and those scatter into the thermal radiation. So actually, the surface layer of the accretion disk will emit a spectrum that is rich in X-ray, fluorescent, and radiative recombination emission lines that will be superposed like in a sort of continuum. And this is traditionally referred to as the X-ray reflection spectrum, and is characterized by two main ingredients. The first one is a forest of soft X-ray lines, strong K-shell emission lines, and then the shape of them encodes the spin of the black hole. But also the second ingredient is a quantum scattered continuum that is shaped into a hump. So in this method, we are actually exploiting and using the relativistic effects of exposing these lines to stronger gravity and Doppler shifts. And that's how we can also want to infer the spin. Also, geometrically thick, as opposed to geometrically thin accretion flows, can undergo large-scale precessions due to length theory torques, and that will imprint dependent quasi-periodic oscillations, or QPOs, in the observer flux. So that is, when we see the temporal power spectrum of this X-ray emission, these temporal frequencies, or QPOs, must be related to specific frequencies of the underlying accretion. But here is very important. Also, those frequencies should be related to the black hole space-time, and thus must encode the spin information. Now, moving to the gravitational wave spectrum, to a system that is purely gravitational, it lacks the astrophysical part. We are now routinely, or at least the LIGO-Virgo-Cagra collaboration, measuring, detecting gravitational waves emitted from the coalescence of black holes. So when the LIGO-Virgo-Cagra collaboration, LVKC, detects a binary black hole, the waveform carries the information about the spins. Last but not least, a future measurement very close to our hearts in this conference, direct images with BECS. So the event horizon has given us horizon scale images of M87 and Sagittarius A star, and very important implications and results came out of these images, and they keep coming. However, we currently do not have a good value of the spins for these main sources, but we will with BECS, because we know that while changing the spin-off in theoretical models, if we keep the max fixed, it doesn't drastically change the diameter, but the spin do cause changes in the images, both in the intensity and in polarization. And those are the features that we're going to go after with BECS to measure the spin as well. So as you can see, BECS fits perfectly also in this landscape, and is another venue to do that. And I'll come back to this idea in a second. So how are we, and by we, I'm using the royal we, how are we currently doing these measurements? And I think it's fair to say that common law suggests we are in a scenario of a spin dichotomy. And the reason is because results are showing in electromagnetic observations that we mostly see rapid rotators, black holes that are rotating very fast. Whereas in gravitational wave observation, we mostly see slow rotators. This apparent dichotomy very likely is actually pointing to a diversity in black holes, and is a very active research topic. I won't talk much about the formation channels, but it is clear we want to understand black hole demographics across the spectrum. Note, however, that there must be lots of black holes in our universe, and we currently have measured about, 60 to 80 black hole spins through electromagnetic observations, and a few hundreds using gravitational waveforms. That includes the last catalog of LIGO-Virgo-Cagra collaboration. So this is less than 500 black holes in total. So to me, it's at least very unclear if we can really do demographics with these little comparative numbers, assuming we have, 10 to the 7, 10 to the 8 black holes in the universe, and we want to do demographics. So we are indeed in an earliest stage of doing these demographics, but actually it's something that we're very, very interested in. Now, this dichotomy, I want to put it in sharp contrast. I could do that. This dichotomy, I want to put it in sharp contrast because even since the very first spin measurements, which are only a couple of decades ago, people using the continuum fitting method inferred both fast and slow rotators with these methods. And this is papers, for example, this paper is from 1997. And as you can see, some of those sources are rapidly rotating, and others are not. And updated values of these spin parameters are still giving very similar results. However, it is indeed generally true that electromagnetic measurements mostly see rapid rotators, as I just said. So for example, here in this plot, there is an analysis of the entire NuSTAR archive of accreting black hole X-ray binaries, that is not AGNs, those are stellar mass black holes, with the relativistic reflection method. Here, and as we can see, the lowest spin value for a SOR has a mean value of 0.46, and then the rest are actually quite rapidly rotating. However, for example, the value of LMC-X3, when measured using the continuum fitting method, not the spectroscope, not the relativistic reflection as shown here, it yields a very different value in comparison to this one. So for relativistic reflection, it seems a highly spinning black hole, but then for the continuum method, we measure something that rotates slower for the same source. So why do we have these discrepancies? Why is spin so hard to measure? And this relates to how I started this talk. The Noether theorems imply that astrophysical black holes should only be described by these two parameters. But observationally, like when we see a black hole, spin effects are very subtle. And the reason is because the spin doesn't have a direct observable, and we can only infer it through secondary effects. either to spectra or the dynamical signatures. So for example, the two primary X-ray techniques methods demand high quality spectra, accurate these models, so systematic uncertainties in these models or the geometry can bias these spin estimates. Also, when we use electromagnetic sources, because it's full of astrophysics, the sources that we're seeing in many ways are very active, and they can actually change from one observation to another. And clearly, of course, it's not that the black hole spin is changing from one epoch to another one, but then the system can indeed actually change materially from one observation to another because of the astrophysics going around. So our colleagues in the X-ray community are doing a monumental effort and very good work to control as much as they can. And it is expected that for some sources, that high value is actually the correct one. Because in particular, there are some relativistic features in the spectra we cannot explain without having a rapidly rotating black hole in the system. But now, and these days, fast rotators are not unique to these electromagnetic observations. And I will come back to this point in a few slides after talking about measurements with the gravitational wave spectrum. So let's go to gravitational waves for a little bit and then describe these systems. The point here is also tricky. Spin leave only a modest imprint on the spiral waveform. So the dominant gravitational wave observable are the masses, and spin effects enter only at high post-Newtonian order effects or via precession, and these are inherently weaker signal. So let's go quickly over these measurements and consider two masses, M1 and M2. The primary and the secondary define it such that M1 is larger than M2. So here we have a binary, and at leading order, the phase evolution during the spiral depends on the shear mass of the system. And then this combination of masses is something we can measure very well with gravitational waves. At higher post-Newtonian orders, the phase evolution now depends on the mass ratio and the effective spin parameter, the sky effective parameter, which is a mass-weighted projection of the two black hole spin vectors onto the orbital angular momentum direction L. So let's see this in a slow motion and how this chi effective is defined. This scalar quantity is defined. So each of the binaries, they have their own spin vector, whose sum, together with the orbital angular momentum, yields the total angular momentum of the system. And these two spin vectors, S1 and S2, are also very hard to measure. Now, if we move to a schematic diagram of the spin and orbital angular momentum, where we now align the system defined such that L is along the z-axis, and θ1 and θ2 are the respective angles of L and S1 and S2, respectively. This is where we can now define this effective in spiral spin parameter, this famous chi effective. It ranges from a value of +1, when we have both black holes spinning as fast as possible and rotating in the same direction of the orbital motion. It goes to -1, where both black holes are spinning as fast as possible, but in the opposite direction, in the way the binary is rotating. But then a value of 0 of chi effective equals 0 could mean that, for example, the black holes are not spinning, or that the rotation actual is in the orbital plane, or that the black holes are aligned, one is up and the other one is down with respect to the orbital. So the reason is because this parameter is a conserved quantity, at least to second post-Newtonian order, and that means that through the spiral, we can measure it quite well. And it's a convenient and well-measured spin combinations in gravitational wave analysis, so it is often tightly constrained by data, and this is typically what it's reported. But then this implies that the LVKC, LIGO-Virgo-Kagra collaboration, typically, they do not report definite statements about the individual spins. However, this is only true for the spin for these spiral black holes, because gravitational waves do provide a more definite answer of the spin of the final black hole, the remnant. And I will come back in 2 slides. Now, so let me show the individual spins of the recently announced, the latest catalog of LIGO, the GWTC4, which was released only a couple of weeks ago. And in this plot, the y-axis is the magnitude of the spin, and the x-axis is only represented different events in this catalog. And I think there are like 81 events here. And I'm plotting individual spin magnitudes with the mean and 90% credible intervals. As we can see, large uncertainties, particularly on the secondary, the A2, and only a few events where both compact objects are confidently spinning. But of course, there are exceptions, and as I said before, pretty good measurements of the spin of the formed black hole, the remnant. So again, in this plot, I'm only showing the components A1 and A2, but again, when we measure the final one, we do have better answers through gravitational waves. So now let me only show the inferred spin magnitude of the final black hole observed up to the run 03A. And as we can see, we do have pretty good spin measurements of several black holes with gravitational wave. That is the spin of the remnant. To date, as I was mentioning at the beginning of the talk, we might have a few hundred values of spin magnitudes. And as we can see here, there is a clear trend. Most of these values are around 0.7. And the main reason for this is that in a binary black hole merger, the orbital angular momentum is very large, and it contributes significantly to the remnant spin value. And in fact, if we have comparable mass black holes non-rotating and they coalesce, the final one will have a spin of 0.7, even if the two initial ones were not spinning. And this comes from the angular momentum of the orbit. But here, we already see there is a great exception. For example, even to this catalog, which only have this one was up to 2021, there was a very nice exception here. So let me introduce GW19 on 814. And at that time, it was the most unequal mass ratio yet measured with the gravitational waves. And I don't know if this event still holds that record. But let me read a little bit of the abstract of the LBC paper related to this event. So the abstract reads, we report the observation of a compact binary coalescence involving a 22.2 to 24.3 solar masses black hole and a compact object. Mind that there are not same black hole with a mass of 2.5 to 2.67 solar masses. And the reason they don't say for the secondary, that is a black hole, is because its secondary component, it's either the lightest black hole or the heaviest neutron star ever discovered in a double compact object system. And what is important for my talk is that the dimensionless spin of the primary for this particular event, due to its large, mainly due to its large mass asymmetry, is actually tightly constrained. So the primary here has a spin of 0.07. So this is definitely a non-rotating black hole in some sense. But only a few months ago, last summer, LBKC reported fast rotators. So let me now introduce GW231123. These two guys are very massive, but then the point here is that the posteriors of these events show highly rotating black holes. So the primary was around 0.9, the secondary 0.8, and then the final is around 0.84. And despite this event, so this is a rapid rotated observer with gravitational waves, we overall in these catalogs, we still support that mostly of these guys are rotating slowly, aligned spins, and this is consistent with a mixture of formation channels for these binaries. Now, let me put everything together. These measurements, the relativistic ones, for example, with the reflection spectroscopy, and the ones up to the third catalog, GWTC catalog. So, as we can see, these two distributions are clearly different. The spins inferred in the gravitational wave are mostly slow rotators, and and when we use X-ray reflection spectroscopy, they are almost maximally rotating. So this discrepancy could be artificial due to systematics, modeling assumptions, or prior choices. These prior choices also affect the gravitational wave measurements by large. And it could also have physical origins. So that's why there's a lot of people working across the spectrum on this. So now, I hope so far I have convinced you that measuring the spins of black holes is not easy, and that there is a room for improvement across the spectra, and therefore having a complementary channel, as specs will be, is fundamental. In words, actually, of our beloved Daniel Palumbo, there is no way we don't learn anything about something by looking at it very closely. So, for example, there is a huge jump in robustness to astrophysics between n equals 0 and n equals 1, as it was discussed during the first part of the conference a few hours ago. BEX will give us the required improvement resolution capable to give us the photon ring, which in conjunction to ground upgrades will give us a better dynamical range and therefore access to key faint features that encode the spin. As Sol will talk later in this session, we can also leverage the relative astrometry of the rings to measure black hole spin. Polarization is also another powerful tool and a venue that we will have with BECS, and George will talk about this also shortly later today. And most of these methods that I just mentioned for BECS are focused on observations and observables which have some sort of time average on them. But however, BECS will also be able to give us sub-images temporal signatures. And then we can go after, for example, light echoes. And of course, much, much more that we can do with BECS related to measure spin. So I hope I convince you that we currently have several measurements of this very challenging parameter across mass scales and a variety of sources. And then there is a lot of room for improvement. So let me conclude by saying that the next generation instruments will make measuring spin a common and extremely informative practice across the spectrum. And I firmly believe BECS will play a fundamental role in it. Thank you for your attention, and I'll leave my conclusion slide, and I'm happy to take questions. Thank you.
Thank you so much, Alejandro, for a very comprehensive talk. Are there questions for Alejandro? Alex?
Thank you, Alejo. That was a great survey. So from looking at a lot of papers that report X-ray spin measurements, what is your takeaway and the takeaway from the workshop last week? I mean, do we trust the error bars or do they include systematic uncertainties? I've met some people that write these papers and they don't seem themselves to believe in the error bars, but is that depending on the specific method or paper, or what's your view on this?
Yeah, as I said, that it depends. There are sources where they might report different measurements, but here we're talking about very few sources. So it's not that we have a lot of a catalog of this. Now, there are people, and as we discussed last week here at Wake, that they do believe in these instruments. So actually, the survey I just showed you is actually a very comprehensive measurement across 250 spectra. All of them are done with the same type of analysis, treating the data the same, accounting for systematics, accounting for the error. So, and it has updated several values. But again, here, and I think I do believe in those measurements. Some of those, as I said, they will hold. And these sources are very different from what BECS will observe, what gravitational wave observe. And it's a very serious business. And these people, they really know what they are doing. So some of those. So again, you can go and see other papers, but then in the X-ray community, of course, there are people that have pretty good constraints. And as I said, there are features in this spectra, Alex, that if we do not have a highly rotating black hole, then there's no way. Like we don't know any other mechanism. And of course, there is room for improvement. Understand what's the corona, and this happens even in our field BECS or even in gravitational waves. As I show you, we also don't have individual constraints. So it is fair to say, like, as I said, like spin will become a precision probe. And that's why I'm excited working with BECS, because we will definitely contribute.
Thank you.
Any other questions for Alejandro? Michael?
Yeah, maybe just following up on Alex's comment. I guess I'm not quite sure what this means for the X-ray measurements. Do you think that there's some systematic error so that this clustering at high spin indicates that there's clustering at some other spin, but it's just biased upward? Or is this just related to the extreme sensitivity only at the high spin end? So there's really, I'm just wondering if you, in a very general way, could add some unknown systematic uncertainty. Is there something you would still state with confidence about the population?
So one thing I want to say is that, for example, this plot that I'm showing that comes from this recent paper, these are inferences on the population. So what we are seeing here, Michael, is not, for example, histograms coming from gravitational wave posteriors. So this is based on observations. Now we do some population analysis, and this is what we get. And this is also what's happening here. And then once you see individual spins, and then you tell me that, like, so here the spin is all around the place. So one thing to say is, like, this also depends on how we're modeling those populations, and I'm not an expert on that. I can refer to some literature. So that's the first thing I want to say. But the second thing, Michael, is that there is also a selection biases. So we definitely see the most luminous one, and then that's very likely those are highly rotating black holes, and these systems are very different. So, for example, when they got formed, low mass X-ray binary, there are many things that must be happening in the system such that this system exists. So in some sense, to me, the ones that we're observing are actually rare events. So it could be that these guys are rotating very fast. And this is different from what we see in gravitational waves. Their formation is also very different. And this is different from, for example, the formation of M87 or Sagittarius A star. So
Yeah.
I think, as I said, like, the demographics that we're doing right now we just have very few numbers, and this is a rapid changing. So now, if there is a systematic that, as I was alluding, and then just talking a little bit on behalf of my colleagues in the X-ray, it is very hard that you take one of these spin measurements and then just put it to zero. So again, these are different sources, and they are doing the best they can do. There could be systematics, but they are actually trying what the best. There are some people in the conference who are saying, like, I did everything that I could to lower that spin, and I could not do it. If I don't do that, I don't fit the spectrum well. At the CFA, you guys are leading a mission, CRISM, which will do an unprecedented resolution, and results are coming regarding that, and the results are somehow consistent. So again, there are many moving pieces here, the source, the models, but also these guys could be very, very different with respect to the other ones. So